Okay, so next we're gonna look at CBC mode, cipher block chaining, which is probably the most commonly used block cipher mode right now. So it works a bit differently. The block diagram is a bit more complicated. What we have here is initialization vector. This initialization vector has to be random, but it can be public. Usually it's just prefixed to the ciphertext. The first block is usually the initialization vector when CBC encrypted things are transferred. So what we do is we encrypt plaintext, XOR it with this initialization vector, encrypt it, then we have the ciphertext. And now, since the output of this is not distinguishable from randomness, we use this to XOR the output of the encryption with the plaintext of the next block. And then encrypt that, and then chain the blocks together like that. This has the advantage that it just completely erases all patterns in the plaintext. And this is what we need, this initialization vector in the first block, because there's no block to XOR in it. Decryption works the same way, so we decrypt the ciphertext, then we XOR the initialization vector in it, we get the first plaintext block, and we take the ciphertext of the second block, decrypt it, then XOR the ciphertext into this decryption, and then we get the original plaintext. So this is the inverse operation of the encryption, obviously. Well, so there are no patterns left, but what could go wrong? Well, to introduce a type of attack, in the next video I want to show you one property of a CBC mode, that is bit flips. Namely, if we, as an attacker, get our hands on a ciphertext and we flip a bit, for example here, in the last byte, because of the avalanche effect, this plaintext block here will be completely destroyed. There will just be gibberish in it. Because if we change a single bit here through the avalanche effect, this plaintext block will be just completely wrecked. But since the ciphertext gets XOR'd to the decryption of the second block, this one bit flip will propagate and will flip the exact same bit in the last bit of the plaintext of the second block. So how could we use that to our advantage as an attacker? Well, imagine, again, you have an open source web system that uses CBC encryption to store cookies on the user side. And inside we have something like this, some info, which is unimportant, but we can control. Then is the user admin, 0, and then inscription, which is also unimportant. So what we could do now is, well, this is the information, the server encrypts it, so we get this encryption here in hexadecimal. Then as an attacker, we know where is what, but we don't know the actual key, so we can't encrypt in the name of the server. So what we could do is we choose this log information, which is unimportant, that we control as a user, to be almost 2 blocks long. So now this block here is actually unimportant for us. And what we can do now is we flip a single bit in this block's encryption, and now if this block is decrypted, it will lead to complete gibberish in the block. So this information in the log, which doesn't concern you, is gibberish, but the error actually propagates and flips the bit in the plain text here. So in the decryption, what the server will see is that user ADM is flipped to 1, because this bit flip propagated to the next block, as we have seen here. Flip this bit, the same bit is flipped in the plain text block. So this obviously can go wrong. In the next video we'll see how this leads to one of the most common security vulnerabilities in CBC mode usage.